Welcome to a video on feedback, and in this video we will be looking at the transresistance amplifier. So the transresistance amplifier is an amplifier that will take in a current and give out a voltage. So the input impedance should be relatively small for the amplifier to accept a current, and the output impedance should be relatively small to provide out a voltage. So the feedback should decrease the input impedance and it should decrease the output impedance. When the transresistance amplifier feedback topology is shunt-shunt, because we measure voltages in parallel and we mix currents in parallel. So fancy words, shunt-shunt. The gain of amplifier like this is in volts per ampere, so voltage out, current in, and that will tell us that the feedback factor is in amps per volts. Always the inverse. Right. So looking at the topology right here, currents are added in parallel, so everything on the input side will be happening in parallel. So RS right here, amplifier input impedance right here, and the feedback output impedance right there. Everything is in parallel with one another. A load resistor, voltage being measured in parallel, and the output impedance in parallel, like that. So input and output impedance without feedback, everything just in parallel. Right, so the two examples that we will be looking at today is the first one is with op amp. So this is a ground, making this a virtual ground. The output voltage is sitting on that node, thus at this node and across this resistor right here. So this voltage is being measured by this feedback resistor, and this causes a current to be generated in that resistor. So we have a voltage to current conversion going on with the feedback network. Another thing to note before moving on, you would notice that this amplifier looks very similar to the inverting configuration of the op amp. So typically at this node right here, you will have a resistor and then a voltage source. It remains a current input for this amplifier. The only thing when having a voltage source like here is you can do a Thevenin to Norton conversion and you end up with exactly the same configuration. So the input resistor on the inverting configuration of op amp takes the voltage and converts it into a current, which then goes through your transresistance amplifier. That is also why it's popular to use it with photodiodes, which is a current source and a resistor like this. And when using a current source, you will use the inverting configuration just without the input resistor like that, because the input resistor is now the same as that of the current source. Okay, so whenever anyone gives you a feedback problem in a test or exam and suddenly it's a voltage input right here, don't be fooled. It is not a voltage amplifier. It is a transresistance amplifier. But you can convert it later to a voltage amplifier again. Okay, I will show you in the example. It's not on the presentation, but I will show you what to do. Okay, so that is the op amp one. pretty straightforward. The next one, a popular one, is to use a MOSFET, bias it using a current source or ideal current source, and then applying feedback. So you will have a voltage output right here, and it can accept currents going in but no DC. Okay, and this structure is also self biasing. So this is not really a voltage amplifier, it is a transresistance amplifier. So having a feedback resistor to bias a transistor when you're doing one of your normal configurations is not always a good idea, because it is not just a biasing resistor, then it is also a feedback resistor. So it will have an influence on your system. Right. Okay. So the ideal and equivalent structures, you can see that everything happens in parallel on the input, everything happens in parallel on the output side. Just remember that the output of a voltage amplifier, we're going to have a voltage divider on the output for loading effects, and we will have a current divider on the input side. So the rules for finding the gain and beta network. So R in, everything in parallel, R out, everything in parallel. Feedback network, we have a voltage input and we are trying to find the current defined flowing into the network like that. So this will also be some form of Ohm's law, but it's V IF over V out, so it will typically be 1 over some resistance. And the gain is output voltage over input current. Okay, this voltage source, when we are going to have to look into this side, will become a short circuit. That is R11. So when looking in like this, and R22, this short will remain, but we will looking in from this side, and there we have it. Right, so if that resistor is just sitting here, it will again look the same from both sides. So let's go to some examples. So the first one is operational amplifier with the gain of 10,000, output resistance of 100 ohms. There's no MOSFETs here, so we are going to have to look at this loading effect. The input differential is infinite. Our source and load is both at 1 kilo ohm, and our feedback resistor is 10 kilo ohms. Before I move on to doing the problem, if we take what we know about op amps already and do this, take this Norton here and make it a Thevenin, so basically a voltage source and a resistor, we will have minus RF over R S in this case, or RI. So that is the gain that you do know for inverting configuration, and that will be equal to minus 10 volts per volts. Okay, so I need to show you this at the end, that we get to the same result when we are not treating it like a transresistance amplifier. Right, the feedback network. So we have V out. Our current is defined in the wrong direction. So we can use Ohm's law right here. So V out over RF would be our feedback current, but we know that it's defined in the wrong direction, and our feedback network is a current over a voltage, so it ends up to be minus 1 over RF. So it's minus 1 over 10 Ks, and 1 over beta will be minus Rf. Okay, so that means that we have 10 kilo ohms right here. So volts per amp. So it's 10 kilovolt per ampere. That should be the gain of this amplifier. So 10 kilovolts per amp. Or the way that I like to write it is to take this K and move it downwards, then it becomes 10 volts per milliampere, which makes more sense. So 1 milliampere in would provide a full swing kind of output for normal setups, right? So I like to write it in this format. Okay, input. When shorting this side, we see RF looking in. Looking in from this side, we see RF going to ground. So R11 is R22 is 10 kilo ohms, which is our RF value. Right, input impedance, output impedance, everything happening in parallel. So input, we have RS in parallel with RID. If this is disconnected in a virtual ground, so R22 in parallel with RF. Okay, R sig was 1K, RID was 100K, RF was 10K. No, RID was infinite, sorry, my bad. Yeah, RID was infinite. So we technically have 1K in parallel with 10Ks. So 909 ohms. For the output impedance, we have R out of amplifier in parallel with feedback resistor in parallel with load resistor. So 100, 10K, 1K gives us 90.1 ohms. Okay, so that's our input and output impedance without feedback applied. Now let's go over to the gain of this amplifier. So first of all, we are looking at the input differential voltage of our amplifier. So minus AD VID. That would be the output voltage on this side. Right. Now, we have a loading factor on the output side. So since we want V out, we have RF in parallel with R load over RF in parallel with R load plus R out. That is the voltage division on the output side of this amplifier. And on the input side, with voltage division, we would also have the input differential where we are taking our differential voltage over RF, RID, and R sig. So the series combination of all the resistors, and that is when we converted this Theveninly to a voltage source and an input resistor like that. Right, so this is straightforward when it's a voltage amplifier. Luckily, RID goes to infinite, so this whole term is equal to 1. Now, how do we convert this from a voltage to a current is we need to know that, oh, if we have a current flowing in and we have a voltage source, the input differential is equal to the input current multiplied by the input resistance, so Ri that we have right here. So if we plug this in here, we have the current or the input current that we wanted, and we have current to voltage conversion. So we have our gain as minus, since it's on the inverting terminal, minus the differential gain of this op amp multiplied by the input impedance of the amplifier multiplied by the output loading factor here on the output side. And that gives us minus 8.19 volts per microampere. So in other words, minus 8.19 megavolts per amp. That's why I like this kind of writing style. It tells us that for a few microamps we should have a very large output deflection for our amplifier, and the numbers make a little bit more sense than having megavolts per amp. Okay, so this is a huge gain. So doing the conversions, all our impedances should decrease. So our input impedance becomes 1.11 ohms, our output impedance becomes 110 milliohms, and here I did it with a mega, which is the answer that you will get here if you don't do the micro thing. Or else you need to divide this by a micro and divide this by a micro, but you will get minus 9.988 volts per milliampere. Okay, or minus 9.988 kilovolts per amp. Okay, so for 1 milliampere, almost full deflection, and with the feedback we calculated it should have been minus 10 volts per milliamp initially. So this is not far off because we have a huge gain in our amplifier. Now, if you take this minus 9.988 volts per milliampere, so if you take AF and you divide it by RS, you get your gain as a voltage. So this is minus basically 10 kilovolt per amp. Divide by that by 1 kilo ohm, and you get minus 10 volts per volt. Okay, so that is the conversion for the inverting configuration of the op amp. So it's first transresistance amplifier. This conversion is done a little bit later. Right. Second example. This is a perfect bias. So this MOSFET here is biased at 5 milliamperes per volt with an output impedance of 20 kilo ohms. 1 kilo ohm source resistor, 10 kilo ohm feedback resistor. So the feedback resistor is the same as the previous problem. So R11, R22 is both 10Ks, and beta is minus 1 over 10 kilo again. Now, looking at our problem, we can see that we have RS in parallel with R11. Okay, this will disappear in parallel with the input impedance of a MOSFET here, which is infinite, so that we don't worry about this resistance looking in. So our input impedance is our signal resistor in parallel with our feedback resistor, and that is again 909.1 ohms. On our output side, looking here, we will see the output impedance of the transistor and this will be in parallel with R22, which is also RF. So 20 kilo ohms in parallel with 10 kilo ohms gives us 6.67 kilo ohms as our output impedance. Right. Now, the gain here is our transconductance. Right, so let's quickly for a moment convert this to a voltage source. Let's call it Vs. So Vs is sitting here on our transistor's input. So V out would be the transconductance multiplied by the source right there. And the impedance seen here, to convert it to a voltage actually, is RF in parallel with R out. Plain common source configuration, right? The transconductance multiplied by the loading. So RF in parallel with R out is the loading. Right. So with this, we have a voltage amplification. Now we need to convert that voltage amplification to a trans resistance. So Vs here can be converted using Ohm's law. So since we have I in flowing into this amplifier dependent on Ri, we can say that Vs is II Ri and plug it in there. So the gain of this amplifier is minus GMRI, and the loading factor on the output side, and that will be our gain. So minus 50.3 kilovolt per amp or minus 50.3 volt per milliampere. That is how simple it is to calculate the gain here. You just need to remember, oh, we can do voltage amplification when this is a common source amplifier, but you need to convert it, the input, to a current, and voila, you are done. Right. So moving on to the feedback, the input impedance would decrease, so that 909 would become 225.6 ohms. And if we want to determine the input impedance of an amplifier, we know that RIF is equal to R in parallel to R sig. So do the reverse parallel combination to get R in. We get 291.3 ohm as our amplifier's input impedance. Right, for the output, there is also a decrease, so 6.67 kilo ohms divided by this large number gives us 1.655 kilo ohms. Since there was no load, we know that our output impedance is equal to our output with feedback. But if there were an output resistance, it would also have been one of these parallel combinations since it is shunt-shunt. Right. The feedback then minus 7.52 volts per milliampere. That is a bit far off from the 10 volts per milliampere that we want. And that is due to our transconductance here being a little bit too low, or our input impedance here being too low. So if we can have increase in our input impedance or increase in our transconductance, this gain would increase and our final feedback value here would become closer to minus 10 volts per milliampere. Okay, And that's it for trans resistance feedback. Thank you for watching.